Hello all, welcome to Quantastic Academy. Welcome to Quanta series video number 3. In this video we are going to solve a question from Resnick and Halliday. In the earlier two videos we solved questions from JEE mains, which were quite simple to solve. Not a very big task, because the first one was on digital electronics and the second one was on a very easy work done problems. Those two questions were easy, can be solved within 2 lines. But today's question is something that is mind-blowing, because it is from Resnick and Halliday, one of the most famous books, and I highly recommend all of you to solve Resnick and Halliday questions. That is going to help us a lot in terms of opening up and understanding the fundamentals really well. So this is a question from Resnick and Halliday's 6th edition from rotational mechanics. I suppose that it is a sample question or an example question, but yeah, anyways, it is a beautiful question. So before getting into the video, um, I would like all of you to pause the video and give the problem a shot. That probably after that you can resume the video and look into the solutions. And please do make sure to subscribe and like the video. In that sense, that is going to support our channel really well. And without any further delay, let's get into the solutions part. Okay. So what does the question tell? During a jump to his partner, an aerialist is to make a quadruple somersault lasting a time t equals 1.87 seconds for the first and the last quarter revolution. He is in the extended orientation with rotational inertia I1 equals 19.9 kg meter squared around his center of mass. During the rest of the flight, he is in a tight tuck with rotational inertia 3.93 kg meter squared. What must be his angular speed omega 2 around his center of mass during the tuck? Sounds complicated, but such a beautiful question. We all might have heard about the conservation of angular momentum. That is what we should do. There is nothing much great to solve in this question. So you might have seen this kind of an event in a circus, especially when people they jump from ropes to ropes and they perform somersault motion, and there's another person who catches him or her, and it is a really dangerous event or a sport, you could say. This is one among that question. So let's focus on the physics part of it. So what does the question say? There are actually a person who is an aerialist. He jumps, which means he is in an extended position in the first quarter in the sense during the net time is 1.87 seconds. So during the first quarter and the last quarter, he is in extended position, meaning he is in a fully stretched position. Look at this. So fully stretched position. In this position, the angular velocity and angular moment of inertia are omega 1 and I1 respectively in both the cases. The remaining time of flight, which is also said that he performs a quadruple somersault, which means that he is in a tucked position and he performs 4 quadruple somersaults, which means that for the first and the last quarter he is in an extended position, and in the remaining time of flight he is in a tuck in position. Okay, so our goal is to calculate this angular speed, which is your omega 2, during the rest of the time of flight. So very easy question, nothing much great to think about. The first and foremost thing is that we should apply conservation of angular momentum. Conservation of angular momentum. So we know that initial angular momentum equal to final angular momentum, and it is given by I1 omega 1 equals I2 omega 2, right? So from here I can say that omega 1 equals omega 2 by omega 1 into omega 2, right? This is the first equation that we are dealing with. So this one has got nothing to do with the solution, because there are, see, I don't know what is omega 1. I have to calculate omega 2, but I don't know what is omega 1. So I'll need another equation to solve this in a much better way. What else do I have given in the question? It is given in the question that the t net, or the net time of flight, is 1.87 seconds. It looks like 5, I'd rather put it this way. So the net time is 1.87 seconds. Okay, and during the first quarter and the second quarter, he is in an extended position, meaning the theta 1 is the same, because in both the cases he is in extended position. So uh, theta 1 in both the cases be the first and the last quarter, theta 1 equals 1 by 4 plus 1 by 4, because if, see, these two are the first and last quarters respectively. So in this time he is in extended position, so you have to add both of them. So 1 by 4 plus 1 by 4, which is nothing but 2 by 4s, and that is in return something like this. So 0.5 revolutions. Beautiful. Okay, but why do I need this theta 1? Since we know that the time is actually given as theta by omega. In other words, you might have seen this formula somewhere in rotational mechanics. So it is the same formula that we have used here. Okay, so what for it now? I have t. Okay, t net, I'll represent it as t net. So the net time is actually given as t1 plus t2, right? Which is in fact given as theta 1 by omega 1 plus theta 2 by omega 2, right? Okay, I think I'll go to the next page. Right, beautiful. Now I have t net equal to 1 by, sorry, not 1, my bad, sorry. I have theta 1 by omega 1 plus theta 2 by omega 2. Okay, so theta 1 is 0.5 revolutions. Okay, but what is theta 2? How do I find that? Well, it is easy. Like how in the first and last quarter we have found theta 1, similarly we'll find it for theta 2, because the remaining time of flight, which means that excluding the first and last quarter, the remaining time of flight is to be found, which is really simple. And he performs 4 quadruple somersaults, sorry, 4 somersaults, quadruple meaning 4, so 4 somersault movements. So with that notion in mind, I can write theta 2 as 4 minus 1 by 2. This 1 by 2 is the sum of the first and the last quarter. So with this, I think we get something like 4 minus 0.5, which can be written as 3.5 revolutions, right? 3.5 revolutions, and theta 1 equals 0.5 revolutions. Good. So now I have found theta 1 and theta 2. My goal is to calculate omega 2. And in the first equation, which we have calculated initially, omega 1 equals I2 by I1 into omega 2. And now I substitute that in this equation, in our main equation. So I put t net as t. Okay, you can also, it is the same. Okay, t net, you can put it as t, equals theta 1 by, instead of omega 1, I go for I2 by I1 into omega 2 plus theta 2 by omega 2, and this can be written as I1 theta 1 by omega 2 into I2 plus theta 2 by omega 2. And from here I say finally that I take out 1 by omega 2 is common, theta 1 I1 by I2 plus theta 2 my goal is to calculate this one, so it's straightforward now. Okay, it's just mere substitution and pure mathematical calculations that we are worried about. So 1 by omega 2 can be, sorry, this can be written as I1 theta 1 by I2 plus theta 2. Right, now I have all the necessary values with me. So this is 1.87, this is how much did I get? 19.9 into 0.5 divided by, this is something I forgot, it is 3.93, it is 3.93 plus 3.5. now on calculating, therefore we get something close to, let me use the calculator, and this value comes out to be 3.23 revolutions per second. Okay, you don't need to put that S, you can remove that S and you can just resort to revolutions per second. So this is it, this is the answer that we've got. It is such a beautiful question, though it looks complicated. The concept was really simple, just application of conservation of angular momentum and a bit of intuitive logic that we apply just to solve the question. So it is such a beautiful and an easy question to solve. There are tons and tons of questions in Resnick and Halliday that you can solve. So with that note, I think this is it for the solutions. Solution of today's question. Very easy question, easy to solve. The only thing is you have to practice more, and you'll have to understand the concept. So in future videos we'll also solve questions from IE, Redov, and so on and so forth. We'll look into various other physics numericals from other sources, from other examinations and even from other standard textbooks. So not just Resnick and Halliday, we'll also work on HC Verma problems. We can also work on multiple problems that we have. So with that note, I would like to end the video, and please do subscribe, like and share. That will support the channel, and let's meet the next video. Thank you.